we go. Can you see the screen okay? Yeah, okay. This is where we left off, right? We were talking about classical physics and how classical physics, Newton's laws, are one of the fundamental differential equations that are used to get equations like, like this one. Sorry, my layer is not working here. Give me a second. Like this one here, and then we discussed that if you don't have initial conditions, two of them, in fact, because this is a second order, right? This little 2 here tells you it's a second order equation. That if you don't have two initial conditions, you can't tell the person where the ball is after 2 seconds, right? If they drop it from the height of a cliff. Yeah, so we discussed that. That's really important to remember. It's true for all differential equations. You can never get away from it. You cannot actually use the results of your solution to the differential equation, right? So up here is the solution, one in the box. Can't really use it unless it also comes with initial conditions. Now, you might remember that from 115, that this equation didn't have c's in it like this all the time, right? That's because we were very general in 115, and we said let the initial conditions be this. We said let the initial x be x0 at t equals 0, and let v be v0 at t equals 0. And that allows us to do this exact thing that we did here with our other initial conditions, where were these right here. To just write down, do exactly the same procedure, and we get x of t is equal to minus g t squared over 2 plus b0t plus x0. And that should be familiar to you because this is what you use over and over again in kinematics equations. You often will see it without the minus gt because it's for a general acceleration. So as long as the acceleration is a constant, not changing with time or space, this minus gt just means that it was pointing in the minus x direction. Remember, we were funny and we said, let's let x be up and down, right? And this would be just a. And so then the equation is, as long as a is constant, is x equal a t squared over 2. 1/2 a t squared plus v naught t plus x naught, right? You probably remember that equation. But it comes from the solution to a second order differential equation that we went through and we solved. That was pretty messy. Okay. Okay, so let me get my notes out. I don't know why I didn't have them out before. Let's take a look at the difference now in quantum mechanics. I gotta get rid of some of these layers. Well, hold on. All right. Okay. So in quantum mechanics, or quantum physics, remember, quantum physics is dealing with the really small, although it's a little more complicated than that, as we'll see. It is, things can be very, very, very small and have higher velocity. Let's wait till we get there, and I'll tell you. But it's not just the tiny little small. There's other criteria. Okay. Okay. So we also have a differential equation in quantum physics. It is a fundamental equation that we use for everything. Just like Newton's laws, we use them for everything, right? If you want to know what a rocket's going to do, leaving the Earth, you're using Newton's equations. And, the solutions to that for a rocket leaving the Earth are more complicated. But it's Newton's second law that you're using. And then, on the force side of a rocket equation, you're going to have things like thrust, right? You're going to have things like air resistance. There's a lot of air resistance that's taken into account. So really complicated equations that are usually not solved on paper. They're solved with computers. So, but they still literally come from F equals ma, right? From that differential equation. Because remember, the a part is d squared x dt squared. That's what a is, right? Second derivative of x with respect to time. So everything, we use it all the time. It's just it's used for everything. Okay. It just may look very, very complicated, and the solution may be only available via computer. Okay. All right, but what is the fundamental differential equation in quantum physics? So our fundamental differential equation in QM is what's called the Schrodinger equation. And I always forget if it's OE or EO, because it's really supposed to just be O with an umlaut. It's supposed to be O with an umlaut, yeah, instead of these two things. Okay, anyway, Schrodinger equation. And it looks pretty funny, you'll see. It's probably will look very, very unfamiliar to you. Sorry, that's supposed to be partial derivative. X squared plus v of x and t psi. Okay, so this is the Schrodinger equation. It is a differential equation, but it's different from Newton's equations in several ways. One, it has both time derivatives, right? Time derivatives and spatial derivatives. So it has both, whereas Newton's equation only had time derivative, right? It is a partial differential equation. Okay, these symbols, these partials, right? The symbol, the sort of curly d, is a partial derivative, right? So, like for instance, d partial f partial x, right? Does everyone know what a partial derivative is? And Aaron, yeah, you do. Okay, so it's partial differential equation. It has these funky h bars, right, which you probably remember from 215, right? This is h bars. It has this. It is a complex equation. It has I, where I, of course, is the square root of -1. It is complex. So here's another h bar over here, h bar squared. It has this thing here, which is very important. Let's get another color. Oh, no, screen. This thing here, this, if you remember in Newton's equations, we have the sum of the forces, right? That tells us what's even going on, right? Is it a rocket with thrust and air resistance and whatever, right? Is it a mass on a spring with no friction, right? What forces are acting on the particle, right? That's what a Newton's equation, right? Where a Newton's equation, this v of x and t, the function in general of space and time, is the potential energy function. Oops, potential okay. So this guy is related to the forces, so that a particle would be under, right? So remember that you can specify a potential energy function, and you can get forces by taking a derivative, right? So remember, we have in 115, we learned that the forces are proportional to the gradient of a scalar potential, right? Learn that somewhere in there, right? When we had, say, a gravitational potential, or we had a spring potential energy function, or we had electric potential, right? You can get the forces by taking the gradient of that potential. So it's related to the forces. It's just in a different formulation. It's in the formulation that has to do with energy instead of forces. Now, in Newton's equations, right? Newton's equations are actually vector equations. So if I write down Newton's equations over here, it's really F equals ma, or the vector sign, which is really three differential equations, not one, right? And this is F net, right? So to always remember, so sometimes I don't even write F like that, I just write sum of the forces, which is code for F net, right? And sum of, if you sum vectors vectorially, you're gonna get the net force, right? Okay, so this is three equations. For instance, it's the sum of the forces in the x direction is equal to ma in the x direction, which is m, d squared x dt squared. It's the y equation is sum of forces in the y direction is ma in the y direction, which is m d squared y dt squared. And its sum of f in the z direction is ma(z), which is md squared z dt squared. So it's three differential equations in one. And of course, in a particle, like for instance, let's say a rocket, you're going to have, air resistance up. You may have wind forces that are pushing this way, so pushing in the x direction. You may have forces in all three directions, and you have to solve all three of these equations to get the motion of the rocket, right? And of course, the thrust is going in the y direction. So it's three equations. It's a vector equation. So vector equation. Okay. This equation, the Schrodinger equation, is not a vector equation. Okay. All right. Well, let's back up a tiny bit because I haven't really talked about this thing. This thing is the capital Greek letter psi. Capital A, capital with an A, I think, yeah, capital Greek letter psi, psi, like the pressure in your tires, psi, right? We will also be using the little psi, which just doesn't have those bars, okay, lowercase, but not in this equation right now, anyway. Okay, this thing. So what was the fundamental thing we were solving for in Newton's equations? Well, you can look over here and you can see we were solving in like 3 dimensions. Let's just pick one because like the example we just did was only 1 dimension. You're solving for x. You're solving for x of t, right? Whenever you have a differential equation, whatever is being taken the derivative of, like this, right, is what you're after. You're after that. You want a solution that says x equals something. So similarly here, we are after this guy. We want to solve this differential equation to get an answer for psi. Okay. This V tells us, remember, it's related to the forces. We never really think about forces in quantum mechanics because we're using this energy formulation instead. It's just nicer because you don't have to deal with 3 equations. You really only have 1, right? But this V does tell us what the system is. Like, is it a electron in an atom responding to electric forces from the proton, right? Is it just free by itself? Like it doesn't have no one's acting on it. In that case, V would be 0, right? So it tells us, like the sum of the forces does on the Newton's equation, it tells us what system we're dealing with. That's what V does, right? Okay, but we haven't talked about what this psi is. So it's a very special thing. So psi is the fundamental thing, right? And if we have to back up a little, but it is a probabilistic thing. So psi, if we solve this equation, we would get an answer for what is psi of x and t for a given V, given situation. I want to back up 1 second and just tell you that people don't call this the potential energy function. And in your book, you'll see they just call it the potential. Okay? They call it the potential. It's a little bit of a misnomer because, as you probably know, there's, like, for instance, the electric potential. There's electric potential and there's electric potential energy, and they differ by a factor of charge, of Q, right? Of a charge Q. So they're different units, right? One's joules and one's volts, right? So, but it's a little bit of a misnomer, so don't be confused. It is literally potential energy and has the units of energy. Okay, it's just no one calls it potential energy function; they call it potential. Okay. Anyway, in quantum. Okay, so what is this thing? Well, the x of psi of x and t is what's called a probability amplitude. Okay. Okay. Well, what does that mean? Hold on, I gotta find my notes about what I want to go next, and I just lost my place. Give me a second. Oh yeah, okay. All right, so probability amplitude. So that probably doesn't mean a whole lot to you, right? And I just want to point out before we actually go deeper into what this is, that it's not the position of the particle, right? So think about what we do when we solve Newton's equations. We get the position of the particle for all time, right? And, you know, this is a vector equation for x of t, y of t, and z of t, right? We solved it, we get all of those. And we know where the particle is all the time. This is not that. This is not the position of the particle or anything like that. Okay, it's just this weird thing called probability amplitude. So how does it even relate to the particle? Because, by the way, this m is the mass of the particle, whatever particle we're solving our differential equation for. Again, let's say an electron in an atom, right? How does this relate to the position or anything about the particle? Okay, well, let's take a look at that then. So, how do we actually represent a particle at all? All right, well, here's what we can do. And this is called Born statistical interpretation. Okay, so but no one really has to refer to this anymore. I'm just pointing out that you might hear this or see this in the book, but it's just the way quantum mechanics works. It just has a name. Okay. All right. So let's take this guy, and we're going to square it. And when we square it, we have to do it in a certain way, and we're going to integrate it from a to b dx. And I'll talk about what this square thing means, but just because it's a special operation. But it's not just squaring, but we're not there yet. Okay. So we're going to integrate that over this interval a to b, and this gives us the probability of finding the particle between a and b. Okay, so when you solve this differential equation given a certain v and a certain particle mass, you get this psi, and you can now find the probability that the particle will be between a and b. Notice there's no certainty here, right? You can find the probability. Maybe it's really high. Maybe it's 99.99% that it's between, 2 centimeters and 3 centimeters, right? but it's not like where is the particle, right? And that's for a given time here, notice, right? So this is, you know, between given, finding the probability finding the particle between A and B at some time t, at time t, okay? Similarly here, if you want to know where the particle is at some time t, you got to specify a time. Same thing here, right? But you don't get to know where it is. You get to know a probability of it being between one place and another. Okay. All right, let's look at that. Let's look at that, just a graph of that. Okay. Okay. Here on this axis, I'm going to plot this probability density here. Okay. Now, why am I saying it's probability density? If you look at it, right, this has to have units of 1 over the dx, right? 1 over dx or 1 over x has to have units of that squared. So this thing squared has to have units of 1 over dx to make this work out, right? Okay, because probabilities don't have units. All right. Okay, so this psi squared on this x, and this axis is just the x-axis. Okay. Again, this equation here that you see, the Schrodinger equation, is in one dimension here, right? So I just want to point out that when you get to 474, you will be looking at this in 3 dimensions. That just means that instead of just x here, it'll be a function of x, y, and z, okay? And these derivatives, you'll have a derivative here with respect to, say, r or something, which r is a function of x, y, and z. So this is a one-dimensional, should mention that it's a the one-dimensional Schrodinger equation. Okay. And we're only going to stick with that 1 dimensions for this whole class. Never going to go into 2 or 3 dimensions. All right. So let's plot, let's just make up a plot. So we're going to make up a plot of what psi squared might look like. So let's say you know, oh, whoa, that was not right. Sorry, I gotta fix that. I can't do that. It can't ever go backwards on itself like that. Okay. That was a slip of my pen. Okay. All right. So let's just add a couple of points. So here we're going to call this point B. And here we're going to have a little point, little a, and a point, little b. Okay. All right. And I'll make this point capital A. All right. So if we look at the integral that we made already, right, that would be the area under the curve right here between, right? Because we're integrating psi squared between little a and little b, right? So the area under the curve represents the probability, right, of finding the particle. Right? Okay. So you can't really predict with certainty where it is, right? You can say things like the probability of it being at capital B is 0, right? Because that probability goes down to 0 here. But you really can't integrate. You have to, you know, if you want to know the probability of it being at B, you can't really do that, right? Because you have to integrate this function, right, over an interval, right? You can make it really small, very close to B, And you'll probably get a very, very low probability. So if I make, my interval starts here and ends, right next to it, I'm going to get a really small number, but it's not going to be 0, right? But notice that that you really can't predict where the particle is. You have some idea because of the shape of psi squared where it's less likely to be and where it's more likely to be, right? So it's more likely to be over here, isn't it? Because the curve is high here and you get a lot of area under the curve here. Okay. Yeah, so you have some ideas about where it would be, but you don't know where it is exactly. Okay. Now suppose you make a measurement of a particle. Okay, so suppose, get my pink again here. Suppose you measure where particle is. So let's talk about the difference between, calculating something and saying, oh, I have a probability that it's between A and B, right? And a measurement. Okay, so imagine you're in a lab and now you're going to measure the particle. Where is it? Well, it's obviously somewhere, right? After you measure it, you'll have a number. Okay. Now, it's not saying, I maybe should have not really spoken so soon because this is the sort of crux of what we're going to talk about next. If you measure the particle, the position of the particle, and you find it at some position, let's say you find it here at C, okay? So, and you suppose you measure where a particle is and find it at x equals C. Now notice this comes after a measurement. You measure it and then you find it at x equals C. Okay, well, what happened right before that? What does that mean? Does that mean that even though I can't predict that the particle is at C with my wave function, I can't actually predict 100% that it was at C? What does it mean that I just measured it and I found it at a particular place, C, right? Okay. Well, this is kind of a fundamental issue in quantum mechanics that people have argued about for a very, very long time. And we pretty much know the answer now. It's been many experiments in that we know what's going on. And I'm going to just describe to you the different possible answers to the question, where was it right before I measured it? Because you'd think you'd just be like, well, it was at C, obviously, right? Something's wrong with quantum mechanics that it can't actually tell me that it was going to be at C at time whatever, right? Because I measure this and make this measurement at time t equals 0. And quantum mechanics can't tell me it was going to be at C, right, at t equals 0. It can tell me the probability that it's going to be at C, but it can't tell me it was going to be at C at t, right? So here are the 3 possible answers. I'm going to, wish I had more board space, or yeah, no. I'm just going to kill this layer and move and go on. Okay, is that fine with you? Yeah, you good? Okay. All right. So there's sort of 3 possible answers. To this question. All right. One is called the realist. And this one comes straight from our intuition about classical physics, right? Obviously, the answer here is the particle was at C right before. Kind of seems like the most obvious answer. But let's note that this implies that there's something missing or wrong, something wrong with our quantum mechanical theory, with the QM theory, because so far what I've told you is that you solve the Schrodinger equation and then you integrate that square, the square of the probability amplitude psi, and you get a probability of it being at C, or not even a probability of being at C, a probability of it being in an interval around C, right? You don't get a definite answer. It was at C at t equals 0, right? So this implies that there's something wrong, something incomplete. Maybe there's some hidden variables, or maybe the Schrodinger equation needs to be modified or something, right? That's what this implies, saying, well, the particle was at C, because if your theory can't tell you it was at C, which this theory cannot, then it seems like if this is true, right, that the particle really was at C, then something's wrong. Okay, so that's one thing that people were thinking about. 2 is called the orthodox view. And this says the particle is not anywhere. Before you measure. But that somehow when the act of measuring or the act of measurement forces the particle, forces should be in quotes, the particle to take up a particular position. In other words, it's not anywhere until you measure it. And then you will get C with probabilities given by that curve that we had on the other layer, right? According to psi squared. Okay. But think about this for a minute. This is weird, right? This is saying the particle is not anywhere at all, right? It's not the quantum mechanics. This if orthodox was true, it would say there's nothing wrong with quantum mechanics. Quantum mechanics is literally telling you that this particle is not anywhere in particular, right? And it doesn't really have a position at all until you measure it. Okay, so that's some of the weirdness. That's the first sort of glimpse at sort of the weirdness of quantum mechanics. And then number 3 is called the agnostic. And this one is, who cares where it was? Well, I think this is a stupid one, to be honest with you. Or refuse to answer, right? Makes no difference, right? It makes no difference where it was before. But I don't like this, and people don't really take this very seriously. Makes no difference. Because the other 2 really say something about the nature of our reality, right? Okay. All right. Now, which one of these things is the real what people think is true? Well, in fact, it's not just some kind of philosophical argument. Bell, physicist Bell, I think his name was Joseph Bell, he proved with many experiments that have been done over and over again that you can, that the orthodox view is the correct one. So this is how reality works. The particle does not have a position. It is not anywhere before you measure it. Okay? Just, oh, that strikes you as strange because it is very strange. Any questions or comments on this? What do you think? What do you think about it?
It's definitely unusual. I think I've heard something similar to this list of three,
Yeah.
but I always thought it was funny how there's not just like the fourth option of we don't know where, say, like the particle was before it was at this point, but maybe you could just measure that too. The probability of it being somewhere before that point too, based on what you know. But
Well, yeah, you
yeah.
can, but you can never say. But then you're just a chicken and the egg problem, right? So if you say, well,
Mhm.
I could measure at a different time, right? And then I
Mhm.
could measure another time, and now I know it was here in here. But the problem is that if you take one of those measurements by themselves, right, you
Mhm.
can't. It wasn't anywhere before that measurement, right? You see what I'm saying? It's almost like chicken and egg. You're just moving the time back.
Gotcha.
You see what I'm saying? Does that make
Mhm.
sense? Yeah. And it's not like if you measure it, yeah, we have to talk about measurement in a bit, but it's not like if you measured it at time t equals 0, it would be, let's say it was at c, and then you measured it right after that, and it's just, it's a little bit farther out from c, right? It's not like that, right? Look at the curve of the probability that we had on the previous um, layer, right? You could measure it at C, and then it might be way over on the other side of the universe, right? The next time you measure it, because there's probability that it could be out there, right? Yeah. So it's not. I know what you're saying. It's like, well, couldn't we just reconstruct where it is somehow? But that's just not how it works. And this Bell and many experiments since Bell's experiments really proved experimentally that the orthodox view is the correct view. That there really isn't anywhere. It doesn't have that property. It doesn't exist in some sense. I mean, of course, there's a non-zero probability of finding it in all these different places. So it's not like it doesn't exist, although you might convince yourself that maybe it doesn't exist. Right? Uh, but uh, but certainly doesn't have a position. And we'll see that there are many other properties that it doesn't have. There are some properties that it really does have, and we'll be going over what distinguishes the two kinds of properties. Okay. All right. So this is really closely related. This idea of measurement forcing a particle to take up a particular position, right? This idea, and to a very, very famous thought experiment, and it is referenced on the cover of your book, right? What's on the cover?
Schrodinger's cat.
Yep, and see he's like happy and alive here, and maybe just resting, but probably dead, right? So that's what's on the cover of the book.
Had the book for a year and I didn't even realize the back he's
Yeah,
laying down.
yeah. I remember when I taught this class as a teaching assistant when I was in graduate school, and my professor, who was my advisor, taught out of this book. And I saw the cat on the back, and I was like, "Oh, he's not dead, is he?" And my professor was like, "Oh, I think he is." I was like, "Oh." Anyway, I was not happy about that. So, yeah, so there's a very famous thought experiment, Schrodinger cat experiment, that is widely misunderstood. So, does anyone, either of you guys know the story of the paradox? Like, could you tell me the paradox?
I've got like the rough idea.
Okay, tell me.
there's like some kind of poison in the box and it will be released at some unknown time after like something decays, if I remember correctly. And we don't know when that's going to happen. And the box is completely closed. You can't see into it at all.
Yeah.
And so you don't know if the poison's been released or not. So the cat is both alive and dead.
And it's alive and dead according to this your version here because it's somehow a quantum mechanical system or something, right? It's like half-life after. Okay, yeah. So that's what's the resolution to that? Is there a resolution that you've heard of, or is that just that what you hear? So that much,
I can't remember the rest.
right? And Laura, do you remember this at all? No. Okay. Well, it's commonly told, kind of the way Aaron said it, that oh, the cat's half alive, half dead, and the reason that the whole paradox came up in the first place was an argument against the orthodox argument before Bell proved that it was true, right? So people were like, that's not possible. Let's make it. And then they made up this Schrodinger's cat experiment thing and thought experiment where to say how ridiculous quantum mechanics was because a cat can't be half alive and half dead. Now, you're probably like, well, what does that have to do with quantum mechanics that it's half alive, half dead? Well, the reason it has to do with quantum mechanics is kind of like position, right? Where a particle doesn't have, according to orthodox, right? If you're measuring the position and before that measurement, the particle isn't anywhere. It's the same idea here. If you're going to eventually open the box and figure out if the cat is alive or dead, that it's in, it's neither alive or dead, right? That's the idea behind this, right? Behind this paradox that was meant to like debunk this orthodox view. It was meant to be like, oh, look how stupid that is. Like that, there's cats obviously can't be half alive, half dead. So that was the original sort of idea behind the paradox, to kind of disprove or point kind of well, like I said, debunk, like make the orthodox idea kind of bring out how ridiculous it was and how it couldn't be true. Yeah, again, it was before Bell. You still see videos on the cat Schrodinger's cat paradox that don't really quite state it correctly. So we're going to go through it, okay? Because it's actually, there's a resolution to this paradox that has something to do with how you measure, okay? So I'm going to state it a little differently than Aaron did. I'm going to say we have a cat in a box, and let's draw it. I'm terrible drawing, but here's a box. Side view. And inside is a cat. The worst drawer in the world. Sorry about that. And there's a cat, some legs, there we go, tail. All right. And in the box with the cat is some radioactive substance, like Aaron mentioned. And then there's a Geiger counter, which is going to measure the radiation coming off of this radioactive substance. And once it does, it's going to trigger the letting out of a poison gas of some kind. Skull and crossbones, really badly drawn. Okay. Okay, so this is the Geiger counter. Okay. And then there's also a window over here with a drape on it. There's a little drape so that you could pull across the drape if you want to and look inside. Okay, look and see if what's up with the cat. All right. So the way this is really sort of classically told is that you have an atom in here, or some atoms that have a 50% chance. Let's say one atom that has a 50% chance, 50% chance of decaying. In time delta t. Okay, so now you know, given that, you know, if delta t is like 2 seconds, after 2 seconds, you know that there was 50% chance that it decayed. Okay, and the usual statement is that, oh, you know, that after that delta t, let's make it a little longer, like an hour, that somehow that the cat, you know, is in some, according to the orthodox view, some half alive, half dead state, right? Half alive, half dead state. Because it was 50% chance, right? So, okay. This would be the same thing as the orthodox thing, right? Where we haven't looked and seen if the cat is alive or dead yet. We haven't made a measurement, so right before, isn't it half alive, half dead? That's the usual statement of the paradox, right? The paradox. And then the paradox being that, of course, a cat can't be, it really doesn't make a lot of sense for a cat to be half alive, half dead. Okay. So that's the first part of the paradox. And then the second part is that if you, this is another part, if you look through the window, and find cat dead, let's say, you killed it. Right? By looking. That's what the orthodox thing here, according to the orthodox, right? Before you measure, it's not anywhere. When you measure, it forces it to take a stand at a particular place. So here, in the paradox, the cat is in some half-alive dead state, but then when you look and if you find it dead, you killed it, right? Because you just opened the blinds and you made it take a stand. Before you did that, it was in half-alive dead, still 50% chance of being alive or dead, right? Somehow you opened the you opened the drapes and looked and killed it. And maybe you found it alive, but right, and then you can saved it, but right. So that's that's according to the orthodox. That this argument was made to show how ridiculous the orthodox view was. All right, but now we know one that the orthodox view is true, but this paradox is kind of the setup is a little wrong. Okay. All right. So, this is really nonsense. So the way that it's stated now, we know is nonsense because we're really not thinking about what a measurement is. Because the key to this paradox, to solving the paradox and resolving the paradox, right? Sorry, not solving, resolving, is that you haven't really specified what measurement means in a quantum system. Okay. It means something very, very specific. All right, so what does it mean? Right? We know for sure macroscopic systems cannot be in some linear combination of states like this, alive, dead, right? Cannot be in, some linear combination of states. Okay. But if that's the case, what is the measurement that we're talking about here, right? It's not when you look through the window, because that is not it. And the resolution here is that two measurements are very specific in quantum mechanics. And it's defined as such. A measurement occurs at the moment that a microscopic system, in other words, QM system, right? Quantum mechanical system. And in this case, the microscopic system, right? The microscopic system here is the radioactive substance here, right? This is the QM system, the atom that's in the little, right? That's the microscopic system. Okay. So it occurs at the moment that a microscopic system interacts with a macroscopic system. And in that case, that is the Geiger counter. Macroscopic system is code for a classical physics system. Okay. So interacts with a macroscopic system in such a way as to leave a permanent record. Okay, so if we look at the system here, we have the quantum mechanical system, which is the atom. If it decays, the Geiger counter registers that. The Geiger counter is a macroscopic system, right? And the measurement occurs. So the measurement is not you looking through the blinds and killing the cat. The measurement occurs here, between the Geiger counter and the atom, right? So the cat is never in any superposition of states, right? It's either alive or dead once this happens, because what happens is there's a quantum mechanical system in here. The atom itself is in a superposition of I decayed or I didn't decay, right? After an hour. If once the Geiger counter, though, measures, right, something, it is no longer in a superposition state, the quantum mechanics state, and the cat dies if it's measured in an hour. If it doesn't get measured in that hour, the cat's alive at the end of the hour, right? So this is the resolution to the paradox, and it's the crux of that resolution is the definition of measurement, right, in a quantum system. Okay, it's not you looking at through the window. Does that make sense? And you'll almost, and I think it'd be fun if you go around on the web and look at various descriptions of this paradox, right? And see if anyone is actually resolving it correctly, or even stating it correctly. And you can see a lot of different ones that are not quite doing it right, or still couching it as a paradox, right? Still saying, oh, this is a weird quantum mechanical thing, like weird, right? It's not. When you understand what measurement is, there's no paradox, right? So people are still calling it Schrodinger cat paradox as if it's still not resolved. Do you know what I mean? Yeah. So if you go, you'll see like Neil deGrasse Tyson talk about it, and you'll see all kinds of people talk about it without, as if it was still a paradox. Let's just say, it's not. Yeah. It was not. Once the idea of measurement in a quantum system was understood, then it's not really a paradox anymore. And Bell has proven over and over, and many other people, that the orthodox view of quantum mechanics is actually true. Right. So it's not really a poke at the orthodox view anymore. That makes sense? Yeah. Okay. Now, you may have heard the term collapsing of the wave function, right? You may have heard that. So if we go back to our previous slide or layer, oh, that's not it. Where'd it go? That's not it right now. There it is. You can see that, remember, if we measure at C, oops, it doesn't want me to write on that. Give me a second. There we go. If we measured the particle and we found it at C, all right, right after we measure, because we have forced the particle to take a stand, right? Right after we measure, the probability will look like this. This comes back to Laura's idea. Right after, it'll look like this. We collapse the wave function, right? So right after this is C, it'll look like this. But as time goes on, right? As time goes on, it's going to come back to this state, basically, right? Or it's going to go to its new state, because this is at some particular time. So as time goes on, it may go to a whole new, depending on psi itself, right? Psi is a function of x and t. It might go to a whole new thing, right? As time goes on. But collapsing the wave function refers to this process where you measure, and now it's at C, right? Because we just measured it at C. The probability has to look like that, right? Right after. Okay, does that make sense? So, but if you give it a couple seconds, it's gonna look very different. It's gonna evolve with time. Now there are wave functions, of course, that don't change with time. In the sense that, but they certainly would change when you do a measurement. Right? So measurements can affect the wave function, even if the wave function is a static wave function, meaning that has no time dependence. It just sits there. If you measure now, you are interfering with it, and you're collapsing the wave function. Does that make sense? This whole idea of measurement is something we're really not going to continue worrying about. I mean, that's not true, but we're not going to worry about it in the sense that we're not going to worry about the collapse of the wave function, because that kind of idea of understanding the math behind that, what happens, you collapse it, and then what happens after that, we're just not going to use that. We will be talking about measurement a lot, but we won't be talking about the details of the collapse of the wave function. Okay. I think you'll understand at some point, okay, about that. All right, so let's now, since we've been talking about probabilities here, we're going to sort of back up and just talk about probabilities like you'd get in a statistics class, because you're going to need to understand probabilities, some statistics, easy statistics, but statistics that you've gotten in lab classes, and if you took a stats class, it's even better. Okay. Okay. So let's talk about probabilities. Okay. So let's talk about, we're going to start with discrete values. What does that mean? It just means that we have discrete values for the outcomes of something. So for instance, let's say you have a room with 14 people in it, and each of them has an age, and we'll round up to the nearest year, okay, as we do for ages usually, unless you're little and you're like, oh yeah, I'm 5 and a half, right? So we'll just round up. So the ages of the people in the room are, there's a 14-year-old, 15-year-old, 16-year-old, 22-year-old, 24-year-old, 25-year-old, couple 25-year-olds, another 16-year-old, another 16-year-old, 22-year-old again, 24-year-old again, more 25-year-olds. Okay, so this is all the ages of the people in the room. Again, rounded up because we're doing discrete, right? Values. All right, let n of j be or represent the number of people with age j. Note that j is our discrete variable, right? Discrete meaning, right, that it's not a real number. It's not a, you know, floating point number, right? It's like an integer, okay? Discrete. This is discrete variable age. They're representing age. Okay. All right, so let's look at what is n of j. So let's say, what is n of 14? I'm asking you guys.
That would be 1.
Mm-hmm. N of 15.
Also 1.
N of 16. Ah,
2.
wow, I can't. 16. 2, right? Or is it 3? 1, 2, 3. It's 3.
Oh, 3. I missed one.
There's
Sorry.
there's a 6 up there, yeah.
Oh, it looked like a 2.
It did, yeah. Okay. Like 12-year-old, huh? Okay. What about n of 17?
0.
0.
Yeah. And what about n of 22?
2.
2. N of 25?
5.
5. And n of 24?
2.
Yeah. Okay. Now I left off a bunch of ones that are 0, right? Didn't I?
Mm-hmm.
There's no 12-year-olds, there's no 11-year-olds, there's no 5-year-olds, there's no 60-year-olds, right, etc. Okay. Well, let's represent this with something called a histogram. We'll get orange color again for our axes. So here's our axes. This axis is j. This axis is n of j. And we are going to use what's called a bin, right? So histograms usually are usually made for discrete variables, right? Like this, like age, to count how many of each you have, and you put your ages in bins. Okay. Now, sometimes you might say, well, I'm going to make a bin and I'm going to put everybody with ages between 14 and 16 in a bin. So your 14-year-olds would go in there, your 15-year-olds would go in there, and your 16-year-olds would go in there, right? In a bin. But we're going to actually just have each age have its own bin. So let's say we'll start over here at 10-year-olds. Okay. So this is the bin. If you had a 10-year-old, they would get put in this bin. It's 11-year-old, 12-year-old, 13-year-old. It'll take me a minute. Hold on, give me a second. I'll just go to 30 because we know, what the rest of them are. Okay. And now let's fill in the bin. This is what you do for a histogram. It's like a bar graph, okay? So I have one 14-year-old, and I'm going to have this be my height of 1, okay? And I come over here, and I have a 14-year-old, so I make a little bin, I'm sorry, a little bar, a little thing, and I fill it in. Oh, I put that in the 13-year-old. Sorry about that. Let me get rid of that. Go away. And I put it in the wrong bin. Okay, here we go. Okay, let's see. I have a 15-year-old, so I will his little bin here. 1 15-year-old. 16-year-olds, I have 3, so I've got to make my thing go 2, 3. See how high that is. And that's going to have 3 little boxes, right? There's 1 16-year-old, 2 16-year-old, and I did not do a good job of making these the same height, but they should be the same height, right? Okay, 3 16-year-olds, no 17-year-olds. We have to go all the way up to 22-year-olds, and we have 2 of those. 1, 2. Then we have a couple 24-year-olds as well. And we have 5 25-year-olds, so we got to go up to 5 here on our plot. And I'll just get the height. So I'll draw this a little better. Let's see here. So it's 1, 2, 3, 4, 5. And that's what a histogram looks like. Okay, it's a little plot of what the number of your data is, right? So how many of each of the data you have. Does that make sense? I'm sure you've seen the histogram before. Okay. So now, how does this relate to probabilities? Well, it can actually help us. So of course we could have this list to this table here, but you can also just read things off of the histogram, okay? So for instance, if we want to know, if I pick a person at random, what's the probability that they'll be 15? What is prob that a random person in our room, so we pick one of them, what do we do? If you had this just the histogram, what would you do? What's the probability?
One out of 14.
1 out of 14. Right. So you look over here and you're like, oh, there's only one of those guys, right? And I have a total of 14 people, so it's 1 out of 14. What about 16? What's the probability that random person will be 16?
3.
Yeah.
Out of 14.
3 out of 14. Right? Again, you look at the 3. Here's the 3 for 16, and you divide by the total. Okay, so in general, let's define the probability of a person being a certain age, J, as n of J over n, where n is the total. Yeah? That makes sense? Just making it, more formal. So P of J is the probability. Okay. Now, what about the probability of picking one person that we'll get, if we pick only one person, that we'll get either 14 or 15, that we'll get the 14-year-old or a 15-year-old, get a 14-year-old or a 15-year-old. What is that probability?
2 out of the 14 people.
Okay, so how'd you get that?
Because you only have one 14-year-old and one 15-year-old out of the total of 14 people.
Yeah, so you added the probabilities though, didn't you, right? It's the probability of getting a 14-year-old plus the probability of getting a 15-year-old, right?
Mm-hmm.
Yeah, that's right. So you added the 2 of them, and I'm gonna take a picture of this so I can bring it on to the other, to another slide. Okay, I'm gonna get a new layer. Give me a second. Okay. All right. So if we have the probability here of, you know, getting a 14-year-old or a 15-year-old, we add the probabilities. That's going to be P of a 14-year-old plus P of a 15-year-old, right? And that's end up being, just like Laura said, 2/14. Yeah? Okay, well, obviously, what about the probability of getting a 14, 15, or 16-year-old? Right? It'll be probably a 14-year-old plus probability of 15-year-old plus probability of 16-year-old, and that's going to end up being, what is it, 5/14, right? Because this is 3/14. So 5/14, yeah. So you can see we're adding up the probabilities. Okay, well, what is going to be the probability of getting any age? And I mean any age, like 62, 14, 25, whatever. What is it?
I'm second guessing myself, but it would be 14 out of 14, correct?
Yeah, it would be 1. Absolutely. Yep. Because it is the probability of getting someone who's 1-year-old, plus the probability of getting a 2-year-old, plus the probability of getting a 3-year-old, ... right? Plus the probability of getting the 14-year-old, plus the probability of getting a 15-year-old, ... plus the plus the probability of getting a 60-year-old, and on and on, right? ... right? And even you can even just take this sum up to infinity, right? Because after, like, 100 and, well, we're only talking about our room. We only have certain ages in our room, but right, you can still just take the sum out to infinity, can't you? Because they're all 0, right, after 25 anyway in our room. Okay, so this, the probability of getting any age, is equal to the sum. I should have started with someone who's 0, right? Because there are people who are 0 years old. Okay, is the sum of j equals 0 to infinity of p of j, right? And that is 1. And it has to be 1 for this to be for these to be probabilities, because you have to have you have to have when you pick somebody from the room, they have some age, right? So you got to get something. Okay. All right. Well, class is over, and we will. We'll see you. Well, I'm going to see Erin in a few minutes, but we'll see you on Tuesday.
I have a question really quick. There were a few notes that I missed from last class that I was going to go fill in, but you haven't uploaded the classes yet. When can we expect
it's up
those?
now. It was up
It's
last
up
night.
now?
Yeah, it just took a
Okay,
while.
I didn't check this morning.
Yeah. That Thursday, I mean, that Tuesday was really hectic, and it's most likely that I'll get to those the same day, but it's not always the case.
All right, thank you so much.
All right, sure. All right, bye.